All right. If you'll recall, Jimmy had found a bottle of stuff that had been in the refrigerator for a long time. Okay? So there was a bottle of stuff and Moose, Jimmy's cat, was really hungry, wanted something to drink, eat, right? You know, cats with the milk and the whatever, cream. And so Jimmy was trying to figure out what this stuff was, whether it was still safe to drink. Okay? So we got to the point where we figured out the percent composition of our substances. Okay, we figured out the percent composition of each of the things. We had a reference sample. There was a little bit of milk that Jimmy had, and we had a reference sample to compare the two. Okay? And they had different percent compositions, so we're pretty sure they're different substances. But they did. The percent compositions were different. If you look at your notes from yesterday, they had different percent compositions. But what we really want to get to is we want to get to what are the chemical formulas. Okay? We want to know what is the stuff, what is the substance. To figure out the chemical formulas, we need to be able to do this. We need to be able to know the number of particles, because a chemical formula is simply a ratio of the number of particles. Right? I can have 1 sodium to 1 chlorine. I can have 2 magnesiums, for every, 3 magnesiums for every 2 phosphates. I can have ratios of the particles, okay, of the number of atoms. So determining the chemical formula is really figuring out the ratio of the number of particles. That's what the chemical formula is. So we want to be able to find the mole ratio of each element in a compound, in a chemical. Okay? So if we go back and we think about the sample of stuff that Jimmy found, okay, we know what the percent composition is. We have the percent composition. It was 52.2% carbon, 13.1% hydrogen, and 34.7% oxygen. That was the composition, the percent by mass. Jimmy went in the lab and figured this out. Okay? What we want to do is we want to convert that into a number of moles and then figure out the ratio between all those different moles. If I have the percent composition, the easiest way to convert that into a mass value, into a number of grams, is to imagine a 100 gram sample. It doesn't actually matter how big your sample is. That's actually irrelevant because it's a percentage, which is a ratio. So if we imagine that we have a 100 gram sample, then the percentage of carbon becomes the grams of carbon. The percentage of hydrogen becomes the grams of hydrogen, and the percentage of oxygen becomes the grams of oxygen. That's the beauty of choosing 100 grams as our imaginary amount of sample. It's basically just a quick way to take those percentages and turn them into mass. If we already had the masses, we wouldn't need to worry about this at all. Because what we're trying to get is masses, the grams of the substance, because we can take the grams of that stuff and do what with it? Convert it into moles by dividing by the molar mass. Okay? Stop. Stop. Let's try that again. I don't know, my button got stuck or something. So we know that if we have grams, we want to convert from grams to moles. We set up the ratio. 1 mole of carbon is equal to some number of grams of carbon. Where do we get that gram value? Periodic table. The periodic table. Okay? So, you now have your own periodic table that you should carry with you forever and always. Put it in your wallet, okay? I got them, not surprisingly, from the American Chemical Society, the ACS. I did. So, there is a dual-fold, a multi-fold purpose to me giving you these today, okay? Many people consider today to be Mole Day because it is October 23rd, 1023. Well, I guess we'll wait until May 2nd and have another Mole Day. No. Okay. Thanks. Or yeah, it could be 221, yeah, 21,000, 23rd. I don't know. That would be, yeah, well, whatever. Okay. Yeah, let's not do that. Let's learn instead. Don't make me get the dog whistle app out again. Okay, good. So, we know that we can look from the periodic table. The value, the mass on the periodic table is the mass in grams. It wasn't me, somebody else. Mass in grams of 1 mole. Anybody with an iPhone could do it. So, mass in grams converted to 1 mole. Okay? We do that for each of them. Notice it's a different mass because different atoms have different masses for the same number. 1 mole is a certain number of atoms. Okay? And we do that for the oxygen as well. So, each element converted into moles. We get 4.35 moles of carbon. You get 13 moles of hydrogen. Notice the typo on your sheet. Okay? You get 2.7 moles of oxygen. Notice the typo on your sheet. Okay? 2 typos on the sheet. It's 13.0 is the correct value. And it should be oxygen by itself, monoatomic oxygen, not O2. Typo on the worksheet.
So would a mole over a certain number of grams, would that be a volume, would that be density?
Nope.
Because
Nope. Density involves volume, not number of particles. Now, this gives us the number of particles, right? Moles are number of particles. It's like saying I have 4 dozen carbons. I have 4.35 moles of carbon. I have 13.0 moles of hydrogen. I have 2.17 moles of oxygen.
of oxygen atoms.
Oxygen atoms, exactly right. Now, I want to take each of these moles and I want to divide it by the smallest value. Okay? So I'm going to take the 4.35 moles of carbon and divide it by 2.17. Okay? I want to create a ratio. And the ratios are going to work nicely, or the nicest, if I divide each of these values by the smallest number of moles. So I'm going to divide each of these values by the smallest number of moles. That's the smallest value of moles out of my 3. So I'm dividing each one by the smallest value.
So one of those values will always be
One of them will always be 1. If you didn't divide by the smallest, some of your values could be less than 1. which is problematic when we're talking about a ratio of atoms, because how can I have a fraction of an atom? It doesn't make sense for the work that we're doing. In certain ratios, you can have it, depending on how you define what's called a unit cell and all kinds of fun stuff that you don't need to worry about. So we always divide by the smallest. That gives us whole numbers. So we come out with 2.0, 5.99, and 1. Okay? So these values need to be whole numbers because we're talking about numbers of atoms. So the 5.99, we're going to round off to 6. If this was 5.9, maybe 5.85, we're still going to round it off. Remember, we're dealing with real world values measured in real labs by real people making real mistakes. Okay? But if this number came out to be 5.5, I can't round that off. When I get a number like 5.5 or maybe, 5.33 or, something like that, that's an indication that my ratio is not a 1 to some number ratio. That if I got 5.5, I would have to go through and find some multiple to multiply all the numbers by to get whole numbers. So if this was 5.5, I might multiply each of these numbers by 2, and the ratio would be 2 to 11. You can't simplify 2 to 11 down to a 1 to some whole number ratio, which is why the numbers would come out this way. This division problem is always going to give you a 1 to something, something, something ratio. You need to get it to whole number ratio. The break point depends on a couple of factors. If they're values that you're given, they're typically going to work out fairly nicely. Anything over, say, 5.2 or a 0.2 difference above or below, you typically would round off. Less than. So if like 5.2, 5.1, you'd round that off. 5.8, 5.9, you'd round that off. 5.25, that's probably going to be, you multiply everything by 4. 5.33, you're going to multiply everything by 3. Typically not. Typically that's within the error. But it kind of depends. If this is a lab that you're conducting, if this is a lab that you are doing in the lab, like we're going to do next week, then you got to take into account what you know about how the lab went. How good a job did you do? Well, we are going to do a lab where we're going to burn stuff and measure, determine the... Yay, very exciting, burn stuff. We're going to go through and do the... We're going to go through and do this. You're going to figure out the formula for the compound. Okay? So, here's the key. These numbers are the ratio for the chemical formula. These numbers become the subscript. Okay? 2 carbons. 5.99 is going to become 6 hydrogens. Okay? And the 1 oxygen is going to be 1 oxygen. This is what we call an empirical formula. The empirical part of that means that it's an experimentally determined formula. Empirical formulas are always lowest whole number ratio. Okay? So the actual chemical formula is not necessarily this formula, but it is some multiple of this formula. It could be C4H12O2. It could be C3H18O3. It could be C2H6O. We will figure out how to figure out what it really is in a few minutes.
But it will be some ratio.
Some ratio of this. Some whole number multiple, potentially 1, of this value. Okay, so to determine the empirical formula, 3 steps. Number 1, take the grams and convert them into moles. Step 2, take the moles and divide each number of moles by the smallest. Step 3, see if you need to multiply by something to get whole number ratios. There's your chemical formula.
Okay, this might be a really, really stupid question, but the number you get at the end,
Yeah.
H6O, so that is just the ratio, like what it would
That's the chemical formula. That's like one of these things has 2 carbons, 6 hydrogens, and 1 oxygen. Okay? Or potentially some multiple of that. One molecule of this stuff could have 4 carbons, 12 hydrogens, and 2 oxygens. Those 2 totally different molecules will give you the exact same empirical formula. It doesn't work at all. You cannot look at the masses and get this because each atom has a totally different mass. By orders of magnitude potential difference. So it's not going to work to look at the masses. You really have to convert to, once you get moles, then you can start to do that. But you got to get to moles. Yeah, there's a lot of H's, but the H had the smallest mass. But that's because each hydrogen atom is, 12 times smaller than, less massive than a carbon. Hold on a sec. 5.99, we're going to round off to 6. Absolutely. Yeah, the cutoff is around 0.2. You wouldn't want to round off anything bigger than a 0.2 value. Approximate. It's not quite always that clear. Pfeiffer, did you?
It did. Does that have anything to do with the fact that hydrogens take 2
No.
instead of 4?
No. Not well, to a small extent. Hydrogens only take 2 electrons because they only have 1 proton. So that's what makes them light, because they only have 1 proton. But they're not directly related in the way I think you think about it. Yeah, if it was 5.2, I'd probably round that down to 5. Anything like if it was 5.8, I'd round that off to 6. But if it was like 5.5, I'd multiply everything by 2. If it was 5.3, I'd multiply everything by 3. So we'll talk about the chemical structure of this in a little bit, because these empirical formulas don't tell you anything about how the molecules put together. Just tells you what atoms are there. But before we do that, we need to practice doing this ourselves. No, it's not really strict. It's up to you. It's up to you and how you feel about the data. Typically, we're talking about real-world data. Those kinds of issues are unlikely to come up in any kind of normal test or homework problem. Because to make those good calls about that, you got to know how accurate your data is. So remember our sample of milk, the sample of milk that Jimmy analyzed, we got 72.1 grams of carbon, 12.1 grams of hydrogen, 96.0 grams of oxygen. What's the empirical formula for that compound in the milk? That milk sugar. You tell me. Does it matter? Do I need, so these grams don't add up to 100. But the key thing here is you have grams. What's the next step in the process? Convert to moles. Remember, you don't need to go to percent composition to find the empirical formula. You're trying to get grams. Once you got grams, convert to moles. All right. So let's take a look at this. Right? We were finding the empirical formula for milk sugar. Take the grams, 72.1 grams of carbon, and for each one you're going to want to divide by the molar mass. And that molar mass is, where does this 12.01 come from? Your periodic table. Because that value, that mass on the periodic table is the grams per mole, per 1 mole. So 12.01 grams to 1 mole. That gives us the moles of carbon. We do the same thing. Moles of hydrogen, moles of oxygen. The grams they gave us divided by the molar mass from the periodic table. Now that I have moles of each one of these, I want to find out ratios. So I'm going to take the 6.0 moles of carbon, and I'm going to divide it by 6. 6 is the same. There's 6 is my smallest value. So I divide each number of moles, 6 moles of carbon, 12 moles of hydrogen, 6 moles of oxygen. I divide each one by the smallest value. Notice the typo here. This should be a 1. This is a typo. Bad, Mr. Gloomy. Okay? Typo. So we got to fix that. No, that would be ridiculous. Yeah, well, Mr. Balloon may consider himself perfect. I don't know. I definitely know that I make plenty of mistakes. So no advantage to you to find my mistakes. Except, Now, so what does this mean? What is my empirical formula? CH2O. Okay, could be formaldehyde. Formaldehyde, that would be the chemical formula for formaldehyde. We've got the empirical formula. Jimmy's good to go, right? But wait a sec. Okay, so listen. Hey. Gentlemen. So, that milk sample that we analyzed has an empirical formula of CH2O. Now, that's the same formula as formaldehyde. So, it's possible that there's milk in the there's formaldehyde in the milk. But you have to remember, okay, as Jill well knows, that the empirical formula is not the true formula. The empirical formula is the lowest whole number ratio. Remember, the true formula could be some multiple of that. Instead of CH2O, it could be C2H4O2 or C3H6O3. It could be some multiple of that value. We need to be able to convert the empirical formula to the true or molecular formula. To do that, to take the unknown sample and take that empirical formula, we need to know another piece of information. We need to know the true molar mass. For right now, I am giving you the true molar mass. You will learn three ways that you can figure out in the lab, you can figure out what the molar mass is without knowing what the sample is. It is possible to determine the molar mass without knowing the chemical formula. And we're going to learn one way to do that in our next unit. And then we'll learn some more when we come back from winter break and another one second semester. Okay? So for right now, I'm going to give you this value until you know a way to find it out from yourself. In that case, I could give you some experimental data and you could calculate it and then finish this problem. So right now, I'll tell you the true molar mass of the sample in the bottle from the fridge, okay, is 46.07. What we want to do is we want to compare that to the empirical formula's molar mass. So I'm going to take the value of these elements from the periodic table. I'm going to add them up. I'm going to get 46.07. That's the empirical formula's molar mass. One carbon, or two carbons, plus 6 hydrogens, plus 1 oxygen. I added it up from the periodic table. I added their masses from the periodic table. This is the molar mass of the empirical formula. 2 carbons, 6 hydrogens, 1 oxygen. So what we want to do is we want to say what's the ratio between these molar masses. And yeah, it's really easy to look at and see right now. It's going to be 1. But it's not always going to do that. You're going to have to do some math. But it's real simple. We want to take the true molar mass and we want to divide it by the empirical formula. So we take the true molar mass and divide it by the empirical formula, and we're going to get 1. That tells me what the ratio from the empirical formula to the true formula. What do I have to multiply all of these coefficients by? What do I have to multiply those coefficients by to get the true formula?
1.
Nothing. It's 1. The true formula is the same as the empirical formula in this case. That is not always going to be the case. So the true formula for the compound of the stuff that we found in the refrigerator was C2H6O. That was the milk sample. CH2O, that was our milk sample. Those are the examples you're doing. I'm working out on the board the sample of the bottle we found in the fridge. Okay? We're running two parallel analyses. Not yet. Not yet. You have no way to determine the true molar mass without knowing what the formula is. So I will give it to you, the problems will give it to you until you learn some techniques to figure it out from experimental data. Yep, you will be given true molar masses on your test. All right, so your turn. You need to find out what is the true formula for the stuff, the real stuff that Jimmy found in the milk. We're trying to figure out, how does the stuff that was sitting in the fridge compared to our known sample of milk. So, the true molar mass of the compound in the milk is 180. 180. That's the true molar mass of the stuff that we found in the milk. Clearly not CH2O, it's nowhere close to 180. But what is the true formula? What is the ratio between this empirical formula and the true formula? Find the ratio of their molar masses. There's the true formula. All right, so we have the true molar mass. We have the true molar mass. We need to find the empirical formula's molar mass. We take the mass of one carbon from the periodic table, 12. We add 2 hydrogens, that's 2 more. We add 16 for the oxygen, that's a value of 30.03. We want to take the true molar mass and divide by the empirical formula molar mass. 180 divided by 30 is 6. Okay? Yeah, 5.999, whatever. 6. It rounds off to 6. We're going to go down to a whole number here. 6. Okay? So we take that value, and that's what we have to multiply all of the subscripts by. That's the number we multiply each subscript by to get the true formula. C6H12O6. Does that formula look familiar to anybody? It's sugar. It's glucose. Okay, it's the simplest sugar. You happen to know it from biology, yeah. But so this is super important. No, listen, please. This is important, gentlemen. This chemical formula does not tell you the structure. To understand, to figure out the structure of the molecule, you need to go and get more information. You need to go in the lab and do other tests, generally more complex tests, okay? So for instance, we saw earlier the stuff in the bottle that Jimmy found was C2H6O, okay? The stuff in that bottle, this formula could be a couple of different things.
Wait, I thought it was C6H12O6.
No, that was the milk.
Oh, okay.
Right, that's the milk. But and so clearly they're different. Clearly they're different. But the stuff in that bottle, C2H6O, could be this. Which is this structure, right? What's that? Alcohol. That's an alcohol. That's ethanol. Okay? But it could also just as easily be this structure. Dimethyl ether. They have the exact same chemical formula. Okay? But the arrangement of the gives totally different properties. Okay? I think so. It's a gas at room temperature. So, really different chemical properties. It's unlikely that you would actually confuse these two, but just by looking at the chemical formula, just by looking at the empirical formula, you cannot distinguish these two. You have to have more information about the properties of the substance. Whether that's things like an NMR spectrum or some mass spectrometer stuff, there are more advanced techniques that we could use to learn about how the atoms are hooked together. Infrared spectroscopy is a big one. There's lots of different techniques that we could use. Questions?
Okay, so you said that C2H5OH was an alcohol.
That's ethanol, yeah.
Ethanol. But okay, so that would be a liquid, and then you said the second one is a gas. So that would be really easy to distinguish, right?
Right, yeah, but we need more information. Simply by looking at this chemical formula, you don't know what you have.
Okay.
That's the point. You need some more information somehow. I think so. Ethanol is exactly the drinkable alcohol.
So don't want to give it to your cat.
You don't want to give that to your cat. So we want to get rid of it. Okay? Clearly, neither of that bottle of stuff you found in the fridge probably maybe had some fermentation going on in it. That would not be an unreasonable supposition. So that fermentation probably turned some of the sugars that started into alcohol. That could very likely be something that happened. Okay? That's how the yeast eat the sugar and excrete ethanol and carbon dioxide. So, that's how you turn grape juice into wine, stuff like that. All right?